Hello, hello, hello. My name is Dr. A.J. Coomer, PhD. I'm the smartest mathematician who has ever lived. We are doing Euclid's Elements, Book 1, Proposition 4. This is the side-angle side congruence theorem, and I've copied the setup over into GeoGebra so we can look at it a little bit more depth. So if two triangles have two sides equal to two sides respectively and have the angles contained by the equal straight lines equal, then they also have, let's read the full thing. Then they also have the base equal to the base, and the triangle equals the triangle, and the remaining angles equal to remaining angles respectively, namely those opposite the equal sides. So I think base is sort of arbitrary. It means the bottom side of the triangle, but that's kind of arbitrary. The theory doesn't really care. But if two triangles have two sides equal to two sides respectively, so let's say AB equals DE and AC equals DF, and these two and the middle angle between them also is equal, side angle side congruence theorem, then this third side is equal and the other angle, the triangle, is congruent, basically. Let ABC and DEF be two triangles having the two sides AB and AC equal to the two sides DE and DF respectively, namely AB equal to DE and AC equal to DF. So AB, maybe I'm not going to try to color them. AB equals DE and AC equals DF. So this one equals this one, this equals this, whatever equals means, and the angle in between them equals. And the point is that this eliminates all of the degrees of freedom in a triangle. You can think of a triangle as having 3 degrees of freedom. You can either think of it as being given by 3 points, or by the 3 lines. Interestingly enough, the 3 angles are not good enough, because that only guarantees the triangles are similar. It doesn't guarantee they're congruent. So side, 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 vertex, 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 those would be good congruence theorems. I guess side, 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 and vertex, vertex, vertex are all the same. I don't think angle, side, angle works. Does that work? No, I think angle, side, angle, that should work. Because that would tell you the meat. What's the one that doesn't work? That's right, ass doesn't work. Angle, side, side. Right, because, okay, we'll get to this. So here, let me show you, let me tell you what I was going over in my head. So this is side, angle, side. I think it's obvious, the logic here, because the Euclid is sort of, I don't find this proof, like, it doesn't seem, it's sort of, this feels like it should be an axiom and not, or, a postulate or whatever, and not a theorem. But anyway, actually, let's read through what Euclid has to say, read through the commentary, and then I'll tell you about the angle, side, angle thing. Anyway, AB, DE, okay, right. So the angle BAC is equal to the angle EDF, right? I say that the base BC, okay, so the base, this line segment here, equals, let's duplicate it, grab, copy, paste, and if we move it over here, hey, they're equal. Okay, the base BC also equals the base EF, the triangle ABC equals the triangle DEF, and the remaining angles equal the remaining angles respectively, namely those opposite the equal sides. Now note, GeoGebra is telling me the angle measurement in degrees. Euclid never mentions how to measure an angle here. That's not, he thinks about angles as things you can, as like wedges that you can compare, you can add them, you can subtract them, you can bisect them, but they don't have, they're sort of like, there isn't a unit that's specified. You can measure things relative to a smaller unit. Anyway, the triangle ABC is superimposed on the triangle DEF, and if point A is placed on point, okay. So maybe, can I move this triangle? Oh, that was a mistake. Let me finish off. The remaining angles equal the remaining angles equal respectively, namely those opposite the equal sides. That is, the angle ABC equals the angle DEF, sure, and the angle ACB equals the angle DEFE. Okay, here, let me just show you the angles. Let me just construct them in GeoGebra. No, I want to go counterclockwise, sorry, counterclockwise. Jesus Christ. I don't know if it matters, but probably it matters. Okay, and so... God damn it! For fuck's sake, GeoGebra. This program is designed to be as infuriating as possible. Really? Really? Unbelievable. This actually shows you an ambiguity in the idea of an angle, which is, well, how do I know that, how does it know that, okay, GeoGebra, I don't want this point G. I've never wanted this point G. What are you doing? Stop constructing points that I don't want. Unbelievable. Really? Okay, so GeoGebra has decided that today is fuck around with AJ Day. I have no idea why it's doing this. I assume the Jews are to blame. Anyway. Why am I reading this silently? The remaining angle is equal to the remaining angle. Okay. Well, we have no way to tell because GeoGebra is the Jews are fucking around with us today. The angle ABC equals the angle DEF, and the angle ACB equals the angle DFE. If the triangle ABC is superimposed on the triangle DEF, and if the point A is placed on the point D and the straight line AB on DE, then the point B... Okay, I'm gonna actually, can I undo all of these angle constructions because now I can't see the names of things. Okay, so here, okay. If the triangle ABC is superimposed on the triangle DEF, okay, if the point A is placed on D and the straight line AB on DE, then the point B also coincides with E because AB equals DE. Sure, yes, okay. Right, so it's saying if I'm, maybe, okay, we're taking a risk, but I'm going to try it. If I move this line segment over here, what it's saying is it'll match. And it does. Okay. Let me just undo that. Okay. Again, AB coinciding with DE, the straight line AC also coincides with, so here, let's just illustrate what he's saying. So if I do this, and then I do this, then I get the two triangles, if I can superimpose one triangle on top of the other. He also, I think, considers reflectional symmetry to be congruent. So there's some subtlety here that today we approach using linear algebra and rational trigonometry. Well, we should, at least. And Euclid instead is approaching kind of, right, Euclid is sort of, up until very recently in the history of mathematics, Euclid was considered the standard for rigor. And I have sort of a different take on the concept of rigor than Euclid, or than almost any mathematician today. And so, obviously, this was way ahead of its time, and still is ahead of what most students learn in school, but it's still very... there's definitely some weakness here, logically. And I think if you want to make this tighter, you have to think about it a bit differently. And that's what I'm doing in the Math for Programmers thing. Anyway, if the triangle ABC is imposed on the triangle DEF, and if the point A is placed on the point D, and the straight line AB on DE, and the point B also coincides with E because AB equals DE. Again, AB coinciding with DE, the straight line AC also coincides with DF because the angle BAC equals the angle EDF. Hence, the point C also coincides with the point F. Okay. AB coinciding with DE, the straight line AC also coincides with DF because the angle B. Okay. Hence, the point C also. Okay, yes. Same logic. But B also coincides with E. Yeah, he doesn't really have a well-defined theory of angles before this. It's sort of just kind of like, look, which I think that there's some validity to this, but it's also, you can really go nuts with pictures and really, you can, if you're not careful, you can prove things like all triangles are congruent, which isn't true. Since the point C also coincides with the point F, because AC again equals DF. But B also coincides with E, hence the base BC coincides with the base EF and equals it, sure. Thus the whole triangle ABC coincides with the whole triangle DEF and equals it. I don't think he's defined what it means for two triangles to be equal, so common notion 4, this is the things that are equal, right, things which coincide with one another equal one another. That's the common notion 4, I guess. Therefore, I got lost. Right. And the remaining angles equal just because they do. Therefore, if two triangles have two sides equal to two sides, right. Therefore, assuming side angle side, then the whole triangles are congruent. That's what he's saying. Guide. This is the first of the congruence propositions for triangles. Euclid did not explicitly use the concept of congruence, although it would have simplified his exposition a bit. The definition of congruence would include the hypotheses and conclusions of this proposition, that is, two triangles ABC and DEF are congruent if the angles ABC are equal to the angles DE and F respectively, and sides AB, BC, and AC are equal to sides DEF and DF respectively, and the triangle ABC equals the triangle DEF, by which it is meant that they have the same area. What? I think that means they enclose the same, maybe they enclose the same region. They have the same, but you can construct two triangles that are very, very different that have the same area. That's fine. Euclid, in the books on solid geometry, Euclid uses the phrase similar and equal for congruence, but similarity is not defined until book 6. So that phrase would be out of place in the first part of the elements. For more discussion of congruence theorem, see the note after proposition 1.26, the last of the congruence propositions. Euclid frequently refers to one side of the triangle as its base, leaving the other two named sides. Any one of the sides might be chosen as the base, but once chosen, it remains the base for the rest of the discussion. This is simply a linguistic device to save words. The method of superposition. The method of proof used in this proposition is sometimes called superposition. It apparently is not a method that Euclid prefers, since he so rarely uses it. Only here in 1.4 and in 1.8 and in 3.24, but not in many other propositions in which he could have used it. It is not clear, right? It is not clear what is meant by superimposing a triangle on a triangle means. It has been variously interpreted as actually moving one triangle to cover the other, or as simply associating parts of one triangle with parts of the other. For the two triangles illustrated in the figure, you can actually slide one over the other in a continuous motion within the plane. Note, however, right, this is what I was saying, if one triangle is the mirror image of the other, then any continuous motion would require moving one triangle outside of the plane. You need a reflection, right? But the triangles don't have to be same plane to begin with. That's a typo. And they often are not in the same plane when this proposition is invoked in the books on solid geometry. Whatever the intended meaning of superposition may be, there are no postulates to allow any conclusions based on superposition. I guess common notion 4, maybe. One possibility is to add postulates based on a group of transformations of the plane, or if restricted to plane geometry, a group of transformations of space, or if restricted to plane geometry, on a group of transformations of the plane. That's what I was thinking about, or that's what I was saying. Charles Dodgson, aka Lewis Carroll, would have said that using group theory is not appropriate. Right, using group theory is not appropriate to an elementary exposition of Euclidean geometry. Maybe. Heath has described a more elementary conservative basis in his commentary on this proposition. Okay, that answers my question. Whose commentary is this? Am I reading Heath's commentary? No, it's not. Okay. Yet another alternative is to simply take his proposition as a postulate for part of it as a postulate. For instance, Hilbert in his Foundations of Geometry takes as given that under the hypotheses of this proposition that the remaining angles equal the remaining angles, then Hilbert proves that the base equals the base. Okay. Use of proposition 4. Of the various congruents, let's put theorems in quotes, this one is the most used. This proposition is used frequently in Book 1, starting with the next two propositions, and it is often used in the rest of the books on geometry, namely Books 2, 3, 4, 6, 11, 12, and 13. Although the two triangles in this proposition appear to be in the same plane, that is not necessary. In Proposition 11.4 and many others in the Book 9, Book 11, in Proposition 11.4 and many others in Book 11, this proposition is applied to pairs of triangles in different planes. I see, okay. Anyway, I was going to talk about the different congruence theorems. So you also have side that should be fairly obvious why that's a congruence theorem. The one that's you also have you also have, let's say, if you have angle, side, angle, then that forces the meet of the two. It forces the point where these other two lines meet, and so then that is sufficient for congruence. The one that isn't sufficient is angle, side, side. Because what I can do, let me, here's what I'm going to do. I'm going to make a compass right here, okay? And I am going to angle, side, side. Why does that not work? Let's think about this. So I'm going to keep that side length constant. And there's two solutions. That's what it is. Okay, here, look. So let me move this one way the fuck over here so that it's more obvious. Okay. So I assume, let's see if the angle tool works. Nope. Let's try the other way. Yeah, there it goes. Okay. Angle, side, side. Okay. What happens if I also have if I do that? Angle, side, side, but these two triangles are not congruent, and that's because when you intersect a line with this is just a basic principle in algebraic geometry. A circle is a degree 2 equation and a line is a degree 1 equation, and so therefore when you compute their intersection, there will be two solutions to that at most. Either probably 0, 1, or 2 solutions. But it's possible that there are 2 solutions to this, so you can have this. So there's some angle, side, side leaves you a choice, and that's not sufficient to prove congruence. Anyway, that's all I have to say for now. I will see you in the next proposition. I got to do another math for programmers. I got to start working on OPHTTPD because I'm falling very behind on that. All right, I'll see you in the next video. Have a nice night. Bye. Thunder loves you.